Now, today we are going to learn about the free body diagram. What is a free body diagram? It's a diagram that tells us about an object and all force acting on it. Okay. About a single object, okay, and acting on that not object was caused by that object. So what happened from somebody outside of it into that object? Now, before we go further into this, we're going to discuss about the special types of object that we know we are going to make into the free body diagram. This is going to be our final objective. But going there, we need to know the components. Okay. So next, we are going to discuss about what are forces, which forces we are going to put in a free body diagram. Now, the body diagram, the first class is tension. Tension is the name for the force connecting to object. And what's unusual about the tension is they always, okay, always object out of that object. What does it mean? Okay, let's say I have two objects and I connect it with tension. Now, what's the direction of the tension? Depends on which object you are making your observation. If object A is your point of view, then seen from A, the tension is going to the right. Seen from A, the tension pull A to the right. But if it is object B, you see them, seeing from object B, the tension is going to the left. This is what makes it a bit unusual. First, they are always going out from the object which we are making our observation. If you observe A, it's to the right. If you observe B, it's to the left. And the second, they can change direction by pulley. Pulley is a circle that can go frictionless through an axis. Let's say here, I have an edge here and here is object B. The pulley here is going to change the direction of the tension. But as you see here, seeing from B, the tension is going up because it's going out of B. The tension here and the tension there is exactly the same magnitude. If this is 5 Newton, this is also 5 Newton. The difference, this one goes up, this one goes right. Okay, that's about the tension that we need to know. But the magnitude of the tension is not going to be changed. Okay, that's about the first class of special classes of the forces. The second class is about weight. What is so special about weight? The weight is about, first of all, the direction. Direction is always downward vertical. Wherever the object is going, is object moving or not, there is always weight going down to the center of the earth. The object may be going up a surface here, up a hill, but the weight is always going down. The object may be on top of a table and the weight is always going down. The weight direction always downward vertical. And the magnitude here, W is M times G, but G has two numbers. It is 10 for mechanics. For this book here, unless otherwise stated, we're going to have gravity as 10 meters per second square. But it is going to be 9.81 for physics. In physics lesson, the gravity is 9.81.
Wait, sir, can you explain about the W equals M times G?
Yes. How to find the magnitude of the weight? The weight is the mass of the object times the gravity. So if the gravity here is a constant, what is the value? Well, that depends on two circumstances. If we are doing it in mechanics, mechanics is more about how are we going to solve a particular problem, the strategy of solving it. So the number is usually round up to 10 to simplify the calculation. We are more concerned about how we solve a problem than the exact magnitude of the problem. So in mechanics, let's say we usually have numbers rounded. A mass is exactly 1,000. The distance exactly 20 meters. We do that because what is more important is knowing the strategy of solving a problem. Once we know the strategy, the numbers may vary. So for most mechanics, the gravity is taken as 10. But in physics, we're going to have them as 9.81 because physics is more about the reality. Rather than concepts, the physics is about what is the real thing that we have had. What is the real thing that we can observe, we can measure, and in that case, that's 9.81. Okay, the direction always downward vertical. The third one here is normal contact force. As the name suggests here, normal contact force only present if we have any contact with a surface. So if an object is in contact with a surface, then that surface is always pressing back to the object. The press back by the object, we call them the normal contact force because it is always calculated as being perpendicular. I repeat, if there is a surface and an object is in contact into it, then this object will be pushing it back outside of the out of the surface. The pushback is always perpendicular and the normal. In mathematics, normal means perpendicular or 90 degrees. Yeah. The symbol for the normal contact force is a little bit different. In our book here, most of the time we are going to put them as R. But in some other books, you will have the normal contact force designated with the number N. I repeat, in this book here, in the mechanics book, the symbol for the normal contact force is going to be R. Unlike weight, that invariably written as W, and tension, they have the symbol of T. For the normal contact force, the symbol is not that established. So we can use either R in this book or some other books, they're going to have the number N. Normal contact forces cannot be found out directly. It has to be found by the equilibrium on the y-axis. We need to calculate sum of the forces on the y direction. Because normal contact force is normally on the x-axis, here, perpendicular to the x-axis. So we will need to have them on sum of the forces on the y direction. It's going to be part of the sum of the forces on the y direction. Last one. Is friction. Oh, for normal contact forces, please be advised that it is perpendicular to the surface area. So the direction of it depends on the direction of the surface. If we have an object that is vertical surface area, then the R is going that way. If the object is in contact with a ceiling, then it's going downward. Although normally you're going to have a surface that is downward and object going up. By far, this is going to be our most normal condition. But these two is possible, depend on the situation. What is more important is it is always perpendicular to the contact between the object and the surface. The last one of our series of important classes is the friction. Friction has two types, static and kinetic. A static friction is the friction you have when an object is not moving. Object is initially at rest and we try to force them. We try to push them. Now, the force here, the friction, is going to increase, depend on the push we have. So, we call them F static, and the value is less than or equal N times mu static. Fs is less than or equal to N times mu static. So mu static, this is the letter mu. It looks like Y here, but the long one is before it. This is the Greek letter mu. That is the symbol for the coefficient of friction. Coefficient of friction here is going to increase as the forces that try to go in is also increasing. Here's what I mean.
Sir, can you explain static again, sir? I still don't understand.
Yeah. If you have an object, a box that is standing still on the surface, you try to push them with a force F, for example. Now, at the same time, this is going to be opposed by the friction. Friction, which is static. Check how we are going to write the friction. Friction is normally written as belonging at the surface, not up here, but at the surface here. So the friction is going to...
Sorry, sir. I think it's more towards the problem of the audio.
The problem of the audio?
Your audio is, I think, pretty bad. Yeah, it's a bit choppy.
Okay.
Sorry.
The friction here, maybe you already feel that if you push something heavy, unless you push it strong enough, the object is not going to move. Sorry guys, I think I have just been disconnected. Is everybody here?
Yeah.
Okay. Sorry, I think I was disconnected just now. What happened? Yeah, I'm trying. Okay, good.
So what's the formula for static, sir?
The static doesn't have any formula. They're just going to, the mu static is it will be given by the problem. Just we know, the more rough the surface is, then the friction is going to be bigger. So, if an object is initially not moving, if you push them here, the object is going to push you also back just the same with you. Until that object not moving. You push it stronger, they're going to push you back stronger, just enough to counter you. That's why the symbol is less than or equal to. But once
F
you're
F
strong enough,
F what is equals to
sorry,
F F is less than or equal to what?
yes.
And
And
mu.
is here, the normal contact force, the number 3 here. Normal contact force times the
Okay.
mu s. Mu s is the coefficient of friction, static.
Okay.
Now, maybe you can feel that when you try to push something, initially it's very hard. The object is pushing back at you. But once you can make the object move, you will feel that the pull back to you, the pushback from the object is going to be smaller. And that is what happened in real case. The F kinetic, on the other hand, is always static. The static friction, on the other hand, is a constant. No matter how strong or how weak you are going to push something, as long as the object keep on moving, then the friction is going to be constant and the direction is always against the motion. So our friction here happens only if we have normal contact force. So if we don't have normal contact force, then we don't have any friction. One way for people to avoid having friction is to not having any contact. The extreme cases is the bullet train, the TGV in France or the Shinkansen in Japan. How can they move so fast and also so smooth? Because they do not have any contact
Yeah,
between surface, the
yeah,
rail,
it's only like yeah.
the whole train is simply hovering on top of it because of the magnetic force. And that enables them to move faster because then there's no friction at all. There's only drag by the air. And drag is much smaller than, friction. Okay, so this is the 4 phases of spatial forces that we need to know about them. One thing about the friction, the direction is always against motion. Against the tendency to move. If you try to push an object to the right, the force of friction tries to move you to the left. If you try to push an object up a slope, then the friction is going to go in down the slope. It is always against tendency to move. Of course, if it's moving, it's clear. Okay? But sometimes, if an object is not moving yet, static friction, we want to find out where is the direction of the friction, then we need to calculate where an object is going to move without the friction. Then the friction will be against them. Okay.
Sir, kinetic is like what, sir?
There's a special process of motion.
Kinetic friction is like what?
Sorry?
Kinetic friction. Kinetic friction.
Kinetic friction is the friction that happens when an object is in motion. So if an object is initially not moving, the friction we call them static friction. When that object starts moving, already moving, then the friction change into the class that we call kinetic friction.
Okay.
Okay. So bear in mind, we need to check out which type of friction it is that we are going to encounter. Next, before going further, I want to know first about the axis. Now, the main part, x-axis, is where the object has the main direction of object. Where an object is mostly going on, we call them that the x-axis. And the y-axis is the perpendicular of x-axis. What does it mean here? If we are going on if an object is going to move on the surface, then we are going to see this as x-axis. And perpendicular there is going to be the y-axis. Write this on your paper. That is what we call legend. Legend person, not people. What is it that we are working with? If you have an inclined surface, if object is going either up or down, then that direction is going to be the x-axis. Perpendicular into it, we have the y-axis. If an object is going up and down, then that is x-axis. And perpendicular into it, that's y-axis. If object is falling by gravity, for example, then this is x-axis, the main way that an object is going to move. Moving left or right, it's going to be the direction here. If we throw an object sideways, okay, you throw an object sideways, then this is the main way of moving. This is x-axis, and this is going to be the y-axis. So axis of motion is the main direction that an object is going to move. If you put an object here, free fall, then that's it. This is the x-axis, even though it's used unusual maybe. If you throw an object horizontally, then the horizontal will be the x-axis. If an object is moving up and down a surface, that surface is x-axis. Okay? Now, why do we have the x-axis motion here? We have to put x-axis here perpendicular. It's important because then the Newton laws is going to apply independently to each axis. As long as the axis is the plural of axis. We have one axis and two axes. As long as the axes are perpendicular to each other, they become independent. So we can apply Newton's laws of motion independently in each of them. Now, what are the Newton's laws of motion? Because it's independent, it is possible for one axis to have the Newton's second law and the other axis to have Newton's first law. Okay, so here we are talking about the Newton's laws of motion. What are them? There are three Newtons of motion. The first Newton of motion is saying that if sum of the forces is zero, if and only if the velocity is constant. This arrow here is bidirectional. It means that we can go from left to right. If we know that the sum of the forces is zero, we conclude that the velocity must be constant. But it can also direct it from right to left. If we know that velocity is a constant, including zero, zero is a constant, then we know that sum of the forces is going to be zero. That's Newton's first law. I repeat, if we know that sum of the forces of zero, we conclude that the velocity must be constant. On the other hand, if we know that the velocity is constant, we conclude that the sum of the forces must be zero. Now, Newton's second law. What if the sum of the forces is not zero? Is Newton's second law. The sum of the forces is mass times acceleration. Newton's second law says that the sum of the forces is the same with the mass times acceleration. But this is the new formula. In the past, we're going to use that's going to be d mv dt. This is the formula that Newton himself wrote in his book. Sum of the forces is the rate of change. d dt mathematically means rate of change. We have that there on the derivative of mass times velocity or momentum. Change of momentum per time. That is the sum of the forces. I repeat, initially, Newton says that the sum of the forces is the same with the rate of change of momentum per time. How fast momentum change per unit time, that is the sum of the forces. Bear in mind that in both laws, we are talking about sum of the forces. This letter sigma here. Okay. This is the Greek letter sigma. Sigma. This is capital sigma, and this is the lowercase sigma.
Sir, actually in the Greek alphabet, sir,
Yeah.
sigma has three forms. So sigma, the capital, and then you have the sigma that you draw for the smaller letter. That's for middle sigma, like the middle in the middle. But then if you talk about the ending of a word, it's a different letter as well. So sigma has three letters in the Greek alphabet.
So in Greek letter, uppercase and lowercase may have a different meaning. Okay. Check yourself.
Yeah, true.
Like in physics, okay, we have omega. Large omega here is resistance. But lowercase omega, this is going to be the radial velocity. This is omega, uppercase and lowercase. Uppercase omega means the units of resistance. We call them ohm. But this is the lowercase omega. It looks like W, but with a circle at the center of them. They are going. That is the symbol for angular velocity, as opposed to the linear velocity. What is Newton's third law? An object is, if an object is giving a force to the second object, then the second object is going to have a reaction, we call them, on the first object. Force given by first object number 1 to object number 2 will be the opposite of the force given by object number 2 to object number 1. If I push this glass board back there, I, number one, give force to glass board, object number two. Then I will feel that the object number two, the glass board, is going to give a force to me, number one, with the same magnitude but opposite direction. The net effect, in this case, there is no motion. Because no matter how strong I push, they are going to push back with the same forces. Be careful here that this is about the same couple of objects. One of the things that students often confuse is if we have a weight and a normal contact force. If an object is at rest, if the weight of the object is, let's say, 20 Newton, means the object is 2 kilograms. If it's at rest, then the normal contact force will also be 20 Newton. Oh, sorry. In this book, we usually use R. But these two are not, I repeat, they are not action and reaction by the Newton's third law. Weight is interaction between the earth and this object. So if this object pulled down by the earth 20 Newton, we know that at the center of the earth, there is also a pullback by the mass to the center of the earth that has W dash, it's also 20 Newton. Now this is action and reaction. The first action and reaction is between an object and the earth. Remember, why do we have mass? Because there is, well, why do we have weight? Because there is the earth. If we go out from the earth on the space there will not be any weight at all. Because there is no earth that pull us into the center. Now, the normal contact force is between the surface here, between the surface and the object. If the surface here is a table, the table pushes the object up. At the same time, then the object also pushes back the surface. If you put an object on a table, of course, the object is pulling the table 20 Newton. For example, right? And because of this, then the table is pushed back to the object 20 Newton. Now this and that are the action and reaction couple, but not between weight and the normal contact force. Okay, with this, you have all the components to learn about the free body diagram. And next meeting, we will be able to discuss in full of how to use a free body diagram. Any question up until this?
No, sir. But for the next period, can we have two mechanics period, right?
Yes.
So what's the next period for?
The second period will be
The next period. What's the next?
Activity-based learning. I already sent you something for you to do on the second period. So the first period,
can we submit it?
Sorry.
Can we submit it in WhatsApp? Because in case there's nothing.
No, nothing.
Or via email. Like there's no math in KISS. Like an online learning.
Your online learning, it doesn't have anything at all for today?
No, it has like the previous subjects, but then there's no math.
No math?
Yeah.
Okay. Then.
I've refreshed it a couple of times.
Maybe there is a change. I already put that. Let me check. Oh, okay.
Okay.
Doesn't really matter. If that is the case here, then I want you to do chapter 2 here, miscellaneous exercise, question 1 until 4. That's it. Maybe it's not.
Chapter 2.
Page 29, chapter 2, force and motion, miscellaneous exercise 2, question 1 until 4. 1, 2, 3, 4. The first 4. Just send on my WhatsApp.
Okay.
Send on the online learning, either this one or the next one. That's it. If you have any question, contact me.
Okay.
Okay, that will be it. Thank you. Okay. By then, it's almost done, by the way.